in the previous lecture. Was I gave you our final example of junction tree construction. Then I moved on to the topic of message passing. Because that is our next step in solving the MPF problem. And in the last lecture I gave you a formula for message passing, and then we looked at an example relating to decoding of the 742 code decoding. And so let me just walk you through some of that once again. So the first part of the lecture had to do with the example of junction tree construction, and that was concluded here. Then I gave you a formula for message passing, okay. and we applied it to the 742 code, and we pass messages on the 742 code as shown here, and eventually we ended up now also I introduced another notion, that is that of a schedule. So you pass messages in accordance with some schedule, and the schedule is a function of how many objective functions you want to compute. If there is just a single objective function that you want to compute, then the right thing to actually do is to orient all the edges in your network towards that particular that local domain associated with that objective function, which is x4 in this case, and then you pass messages, and we did that, and then eventually you end up at a point where you have all the messages that are incoming to your objective function, and then the question is, well, what do you do here? And I said you just multiply them, and that is true, but let me just do the following. I'll come back to this. I just want to state a general principle. So a node is ready to compute its objective function once it has received messages from all of its neighbors. Okay. So in the general situation, there would be a node here, let us say x s I, and there will be messages coming from all of its neighbors, and there will also be its local kernel. So alpha I x s I, and these are all the mu k i's that are actually coming in. These are all the messages mu k I that are coming in from the other nodes, and then all that it needs to do is simply to multiply all of them. Okay. At this stage, the node computes its objective function function simply by computing the product of the incoming messages and the local kernel. Okay. So, in other words, beta j of x j is alpha j of x, I should say x s j, sorry, of x s j times the product of k, the neighbors of mu k j x of s k intersect s j. So, the objective function is simply equivalent to just a product computation. You take all the incoming messages, multiply them, and this. Only thing to keep in mind is that all of these are functions. So, when you actually multiply these as functions and then when you represent functions as vectors, multiplying functions is equivalent to multiplying the vectors component by component, and that is also called the Schur product of a bunch of vectors. Okay. So, towards the end, that is exactly what we were doing. We were computing the Schur product of all the incoming vectors. So, let me just select this page and copy it for our current lecture. Okay, so we have this. So, you can see here what I meant, because the incoming messages are 2 theta 1 plus theta squared from each of these nodes. So, you multiply these together, the local kernel is this. So, what you are doing, you could also view this computation as being 2 theta 1 plus theta squared Schur product, which is the component by component product, 1 plus theta squared component by component product, and then finally you have the local kernel, which is 1 theta. So, you also put that in and you have 1 theta. So, if you take the component by component product, so this is the Schur product. So, it is just the component by component product. So, this is equal to 8 theta cubed 1 plus theta squared the whole cubed into theta, and because theta is small typically in the applications of interest, you can approximate this by 8 theta cubed and then theta at the bottom. Okay, so that's where we ended up in the last lecture. Now, remember that your objective function was really so your objective function, which in this case is beta 4 x 4, was really proportional to the probability of x 4 given the received vector, okay, and given that your vector was part of a code, right. That was how we started out, that was the problem we started out with in the last lecture. You see here we had this quantity as the quantity that we were interested in computing here, this one here, and so that is this. And now what this is saying is, look, this is saying that the probability that, and then the way we've always, I mean, there is a choice of ordering when you are listing the values of a function as vectors. So, this first component corresponds to x4 equal to 0 and this is x4 equal to 1. So, what this is saying is that the likelihood of x4 being a 0 given the received vector is 8 theta cubed, but the likelihood that it is actually a 1 given y is theta, and since theta is small, this number is with much larger number. So, what maximum likelihood code symbol decoding will do at that stage is to declare x4 to be a 1. Okay. Since let me do it on the next page. Since theta is much smaller than 1 typically, the maximum likelihood code symbol decoder will decode x4 to equal 1. And now if you go back to our last lecture, we will see that we will have corrected the error that we introduced across the channel. So, here in this example, this was the transmitted code word. So, indeed the fourth symbol was equal to a 1, but we had introduced an error here, so that the received vector was this. So, what we have been able to do using the single vertex version of the GDL is to actually restore the correct value. Now, a comment. So, in a way I am going back and forth between lectures, last lecture and the present lecture, hope that is okay. I just want to actually make one point here. Let me just yeah, so perhaps I should yeah, so let me just make that point with respect to this figure here. Again, this is from your this is the 12th slide from your last lecture, lecture 26. The question is, well, what is the justification for what you are doing? I mean, you are telling us some steps, you are passing some messages, but what is the justification? The justification is simply this, that the objective function that you wish to actually compute, which is this one here, is here. If you look at it, you will see that what you want to compute is the product of all the local kernels, okay, and then followed by marginalization, which means you want to get rid of the variables that are not of interest in some sense, which in this case are x1, x2, x3, and then x5, x6, x7. The only thing the GDL is saying, well, I understand that is what you want to do, and then, but I am trying to be a little clever in terms of when I marginalize, because node 1 looks and says, look, I have information about node 1 and it passes this here. This node looks at node 4 and says, look, I have information concerning x1, but that is of no interest to this. The brute force way of doing the computation would be to collect all the local kernels, have them passed, and then do the marginalization finally and only finally at the objective node. But the smart thing to do is to do the marginalization wherever possible, because then it reduces the overhead in terms of both computation as well as how much of message you pass, because the message that is passed across here is a function of a smaller number of variables. Okay, and also your computations will actually therefore be simpler, because when you are multiplying, you are involving a smaller set of variables. So, that is the reason why that is exactly what GDL does. So, that also at the same time justifies the procedure. Okay. It tells you that nothing much is really going on. The key property that you are using is that of the GDL. Now, for example, supposing instead of actually trying to compute the objective function at node 4, I was trying to compute the objective function at node 6, let us say, then I would orient all my edges towards node 6. And then here what would happen is that I would marginalize with respect to x1, because this node looks across this gap and says, I have information which is a function of x1, x2, x4, but On the other side I see only x4. So I am going to marginalize with respect to x1, x2. Now the question might arise in your mind, well, if you got rid of all the information of x1, x2, how do you know that it is not going to pop up somewhere here? What if a node here or a node here has information about x1 and x2? Am I not in trouble? But that is the beauty of a junction tree, because if x1 is present here and not present here and present somewhere else, then it has to be present along all the nodes along the unique path joining these two nodes. So the very fact that x1 is here and x1 is not here, once you see that, you can rest assured that x1 will not appear in this part of the tree. So that is what justifies your marginalization at this stage. Okay, so that is another point. Okay, now the next question is, well, okay, so now we have justified how a maximum likelihood code symbol decoding is achieved. So I will just make a very short note about this from the example and the junction tree property. It is apparent by marginalization at intermediate stages of message passing as determined by the GDL is justified. Okay. Now I want to actually repeat the same example that we did here, with the difference that I want to consider, in place of maximum likelihood code symbol decoding, I would like to actually carry out maximum likelihood code word decoding. Okay. We take the same code, but now I am interested in maximum likelihood code word decoding. So the question is, what changes would be required in order to enable us to do that? And so as I pointed out, what you could do is, you could the only change that is really required is that instead of the sum product, the summation sign here, you would carry out marginalization using the maximum operator. Okay. So let us just copy this page onto the current lecture. And talk about maximum likelihood code word decoding of the 742 code using the GDL. And I think in an earlier lecture we had in fact set up the objective function. So let me see if I can actually pull that up. here we go. So, in our 23rd lecture, we had as an example this linear code, and our interest was in maximum likelihood code word decoding of this particular block code. And towards this end, what we had done was we had introduced these quantities fi of xi, and we had defined it like this. And if you break this up, it turns out to end up with an expression like this. So, you end up with this objective function. Okay. So, let us copy this page as well onto our current lecture. Okay. So, for the same code we now have this. So, I guess I can actually with this, this is here for just comparison purposes, so to speak. So, perhaps I will just move this up so that we can readily compare these two quantities. So, if you look at this expression on this page, okay, this is our objective function needed to carry out maximum likelihood code word decoding, borrowed from a previous lecture, and you can see that all the local kernels are the same. You are doing the same computation except that you have a max here, whereas in the case of the maximum likelihood code word symbol decoding, what you actually had here, let me remove this, is the same thing except that you had the summation. Okay. So, given that it is decoding, the change in strategy needed to carry out maximum likelihood code word decoding is almost immediate, and what I will do now is, given this, our algorithms are all going to be changed accordingly. So, what do I mean by that? I mean that in the last lecture we put down an algorithm for message passing, which was given here. Okay. Now, this message passing algorithm assumed that the semi-ring in which you are operating is the sum product semi-ring. So, in fact, this notation summation really stands for the first of the two operations in the semi-ring. So, in the sum product semi-ring, this would be a summation and that is a product. But on the other hand, if you are looking at max product semi-ring, then this summation would be replaced by a max and this product would stay as it is. Okay. So, that is how you should interpret this. And similarly, as we said in the beginning of the current lecture, at the end when you are computing the global kernel, what you do is you just take the product of all of these. So, this product is really stands for the second of the two operators in the semi-ring. So, for example, again since we are talking about the sum product semi-ring, here what we have is the product, but there is another semi-ring called the min sum semi-ring, in which case the second of the two operations is the summation. So, it will actually be adding instead of multiplying. Okay. So, please keep that in mind. So, the notation here is with respect to the sum product semi-ring. Once we are clear on that, it becomes clear how to actually carry out message passing. We can go back to this example. Let us go back to this example and carry on from there. Okay, so here we have the junction tree, and this time I want to tackle exactly the same example, the same setting exactly as before. And see what difference comes about since we are employing the max product thing. So, the first thing that is clear is that your initial messages are all the same. So, I can actually restore them, I guess. I did not need to delete them since the initial messages are all the same. Yeah. So, the messages that are incoming from each of the leaf nodes are exactly their local kernels, and these do not change. And again, let us assume that so the setting is the same as before. So, here so we will do decode the 742 code once again for y equal to 0 1 1 0 1 6 7. Okay, so we had remember we had introduced an error in the fourth symbol, so we will just still carry that over. So, for the same example with the same notation as earlier, the initial wave of messages is the same coming in from the leaf nodes, and the first marginalization that is carried out is actually here. So, the question is, what is the marginalization that you would carry out between these two nodes? In the sum product summaring, you would sum over variables x1 and x2. Here you would actually take the max. Okay. So, what you are going to do is I always feel more comfortable when we have a little bit more space to write. So, let me again copy this over. Okay. So, here we want to focus on the computation indicated by this red line over here. So, I am going to delete some of this other stuff which we do not need. So, the question is, what is the computation that is actually being carried out, and the marginalization that you are actually carrying out here is the max over x1 x2 of p of y1 x1 p of y2 x2 times chi 1 to 4 of x1 x2 x4, and this is our function g of x4. So, exactly like we had last time, we had the summation. So, that means if x4 is 0, then this is going to force that x1 plus x1 agree with x2. And so, when you take the max, what you are going to do is you are going to take the max. So, here for example, you will multiply 1 with theta 1 by theta and take the max of these. Okay. So, here what that would mean is that remember these quantities in vector format are 1 theta 1 and theta 1. So, you are going to multiply these component by component and then you are going to take the max. Now, x4 here dictates that if x4 is 0, it dictates that if x1 is 0, x2 is 0. So, then you would multiply 1 and theta and 1 and take the max. If x4 on the other hand is a 1, when x1 is a 0, x2 is a 1. So, when this is a 1, that is a 1, when this is a theta, this is a theta. So, you take the max of that. So, you will actually end up taking, in this case, the max of, so g of 0 therefore is the max between 1 times theta and theta times 1, which is theta. G of 1 is the max of, and this time you go cross because 1 here forces 1 here. So, it is 1 times 1 and theta times theta. So, this is actually equal to 1. So, the message that is passed here as a result is theta 1. Okay. So, the message that is passed is theta 1. And now we can go back to this figure here and fill in all the messages. So, we have seen here that the message that is passed in here. So, let me try to put a different color here. Perhaps I will try red itself. So, this we have already seen is theta 1. The message coming in here again for exactly the same reason is theta 1. This is also theta 1, and this quantity here is the local kernel. Okay. So, this is the local kernel, and you are going to take the product of all of these. So, at the end what you are going to be left with is the following computation. You have x 4, and from 1 to 4, 3, 4, 6 and 4, 5, 7. All of the incoming messages are the same and correspond to theta 1. Your local kernel, however, is 1 theta. So, the way you should interpret this is that it is saying that the local kernel seems to suggest that you are more likely to be a 0, okay, because this number is larger. However, the messages that are coming in from all these check nodes tell you otherwise. They are telling you are more likely to be a 1, okay, and there are 3 of them. So, what do you do? Well, the GDL tells you need to multiply these quantities. Okay. So, in this case your f 4, remember our objective function we had called, we had denoted that by f I of x I. So, it is f 4 of x 4. Therefore, f 4 of x 4 is equal to the product of all 3, which will then be theta cubed and theta. So, therefore, since you compare in decoding, what you do is you compare between the two possibilities, the possibilities corresponding to 0 and 1. So, again a reminder, this here stands for x 4 equal to 0, this is x 4 equal to 1, and when you do the comparison you see that x 4 equal to 1. So, therefore, even the maximum likelihood decoder, even the maximum likelihood code word decoder decodes x 4 equal to 1. So, in both cases you end up correcting the error. Now, the other question you might have in your mind is, well, okay, You told me how to decode x4 on this graph, but what if I wanted to decode all the others? Well, there is no difference fundamentally, because a node is ready to compute its objective function when it has received information from all its neighboring nodes. So you can work out whatever schedule you want. So for example, here we pass messages inwards and we are able to compute the objective function at x4. Supposing you wanted to compute objective functions at all of 1, 2, 3, 4, 5, 6, 7 nodes. What you could do is you could pass messages in an inward and outward schedule, where the messages first come in from the outside and then go back out. In this way, you will actually find out that you are able to compute all the objective functions. More generally, you could set up a schedule of message passing and ask yourself the question, am I ready to compute my objective functions? Have I received the messages? Have I received messages from my neighbors, and so on, the correct messages from neighbors. Okay, so that is in general what you would need to do. You could keep track of in a sequential message passing procedure. So perhaps I should do this. Let us go back to lecture 26. Okay. So here in general, if you wanted to know when is it exactly that a node is ready to compute its objective function, what you could actually see is what in an inward outward schedule. So let us say that you first pass all messages inward like this. And on the graph you could keep track of who has heard from whom. So let me get rid of this red here. So initially it is true that every node knows its own local kernel. So this knows this has knowledge pertaining to 1, this has knowledge pertaining to 2, and so on. But after these messages have been passed, so we can keep track of who has what messages. So perhaps I should put down in red again. So this knows all information pertaining to 1 and to 2. Once these messages have been passed, this has all the information pertaining to 1, 2, and of course 1, 2, 4. Okay. So it knows 1, 2, and 1, 2, 4. Likewise, this knows 3, 6, and 3, 4, 6, because 3, 4, 6 is a node by itself. Similarly, this knows 4, 5, and 4, 5, 7. Now, once these nodes have had a chance to pass on their information to 4, okay, then 4 has information from everywhere, and that is when it is ready to compute its objective function. Now, so that is exactly what we did just now. But supposing at this stage we were actually to pass messages in the backward direction. Okay. So let us say that my next step is to pass a message like this, a message like this, and a message like this. And you see that I am able to pass a message in whichever direction I choose, because I have heard from all my neighbors. So I am in a position to pass messages in these directions. Now at that stage I have all the information, therefore I am able to pass all the information to these nodes. So on the backward wave, every node, as soon as it hears receives the message, it has complete knowledge. Okay. This has already heard from 2, this hears from everything else to which it is connected. And so you can actually go back and then compute it. So that is on the first, and on the second iteration you can compute the objective function at the leaf nodes. All right. So you can find out more details about this schedule from the paper, which is our reference. For more details on the scheduling, please see the generalized distributive law by S. M. Ajee and R. J. Michaelis. IEEE Transactions Information Theory. This is March 2000, the March 2000 issue. All right. So with that, although there may be small gaps here and there, hopefully you understood how you can actually use the GDL to decode the code, decode a code when there is a junction tree. Just a quick note again without proofs, a note on the complexity of the GDL. Of implementing the GDL. It can be shown that the complexity for the single vertex implementation of the GDL is equal to the sum over all edges Eij of Q of Si plus Q of Sj minus Q of Si intersect Sj, and I mentioned this to you earlier. And this is why when we were actually setting up the junction tree, we wanted to keep this as an objective function to be minimized where an opportunity arose. It can be shown, so this is counting additions and multiplications as operations. Okay. Again, I use the term addition and multiplications, but these really are a reference to the two operations in the semi-ring, which in the sum product semi-ring turns out to be additions and multiplications. It turns out that turns out that the complexity involved in computing the objective function at all nodes is bounded above by 4 times the single vertex complexity. Okay. So it tells you, it gives you a reasonable handle on how many operations are required to implement the GDL. Again, for the proof you can actually consult the paper. I think it will take us more time than we really have to actually go through the proof. So, I somewhat ambitiously put down the title of our lecture as the GDL approach to decoding convolutional codes. So, let us move on to consider convolutional codes next. So, maximum likelihood code symbol decoding of a convolutional code. And we did actually introduce convolutional codes in the context of the MPF problem in lectures 23 and also 24. So, let me go to 24 here, and we looked at this figure here, which actually tells you that which really is is a graphical means of actually depicting the factorization of the joint probability function of the message symbols, the output symbols, and the states of the convolutional code. Okay. And we said that this will factor like this, and that is what this figure is all about. So, this is not our junction tree, it is what is called a Bayesian network. It is a directed acyclic graph that reflects the factorization and nothing more, and that is actually given here. And just as we did maximum likelihood code word decoding of the 742 code, you can also pose maximum likelihood code word decoding of the convolutional code in a similar fashion by introducing objective functions such as these, and if you work through it you will actually get this. And this maximum likelihood code word decoding is what the Viterbi algorithm actually does. However, we will come to Viterbi decoding, and I will actually show you how Viterbi decoding can also be viewed from the perspective of the GDL. What I would like to do today, however, is actually introduce a different decoding technique, which is a decoding technique for maximum likelihood code symbol decoding of the convolutional code. So, for that let me just so I think it is easier perhaps to just write it out again simply. So, our interest here is in actually but I should clarify that We will do this by example, and the example will be the same one that we considered earlier, namely this convolutional code. What do I mean by this? Well, it is sufficiently general, except that just to keep things manageable, I have restricted my attention to 4 message symbols here, okay, a short, in some sense a short length convolutional code. So, we will restrict attention to this. So, perhaps I should reproduce this. Yeah. So, let me say we consider the same convolutional code I think I am writing too close to the edge of the paper. We consider the same convolutional code as before, with the difference that we are now interested in maximum likelihood code symbol decoding. So, that leads us to an expression that is P of u k P of u k given y. I can write it as being proportional to P of u k comma y, which is a marginalization of P of u k, k is equal to 0 to 3 and y, which is a marginalization with respect to u k of, and a further marginalization over the entire state space of the code of P of S k, the state sequence going from k is equal to 0 to 3, u k, there are 4 states, excuse me. K is equal to 0 to 3 and y k, k is equal to 0 to 3. Okay. So, this corresponds exactly to our convolutional code here, where there are these message symbols. This is the state sequence. You start from state 0, end up in state S4, and these are your corresponding received symbols. And that graph tells us how this actually factors. So, you have probability of S0 okay. So, this factors like this, and once again we see that we have ended up with a problem that has the form of a marginalizer product function problem. Okay. And this is where, since we only have 2 minutes left, this is where we will take up our discussion in the next lecture. So, just to recap, what we did today was I started out with the GDL approach to decoding, where you want to do maximum likelihood code word decoding. To begin with, I just made a couple of notes. I explained that how would a node under the GDL compute its objective function, and we completed our discussion of maximum likelihood code symbol decoding. Before moving on to maximum likelihood code word decoding, we made the observation that you simply replace the summation operator by the max operator, and we carried out decoding. So, that was quite straightforward. And then towards the end, we started discussing decoding of the convolutional code. There was also a short note on the complexity of the GDL. Okay. All right. So, thank you. We will see you next time.